So, hello everyone. Today we'll start with a new topic, which is the coupled problems. It's a very important topic in our course. And today I will start with general definitions, and I will give some examples. And I will discuss the idea of coupling on a very simple example, which is spring and mass systems. So 1 or 2 or 3 mass systems with some springs. And this will help us to understand what we mean by coupled and uncoupled systems. So let's start with the first example. So first we have here the thermomechanical problem, where we have as an example this railway with this steel track. And you see here we have an interaction between deformation and temperature. Apparently here, due to the temperature which comes from the sun, we have some mechanical deformations. This could be also permanent if you have plastic deformations in the steel. But the main driving force for this deformation is another field, which is temperature. And the interaction between the deformation and the thermal actions happen not only on the surface, but also inside the material. And that's why we call this kind of problem volume coupled problem. We have another example, which is exactly the opposite way. So due to the deformation, we have increase in temperature. And this can be measured using the thermography. Take, for instance, this uniaxial test, which is applied to a metallic material. So due to the repeating of cyclic loading, unloading, and so on, so you can measure increase of temperature, and this might also lead to the damage of the material. And this is another example of how the deformation leads to temperature increase. So previously, the temperature has led to deformations. Now the deformation has led to increase of the temperature, and this is a typical also volume coupled problem. So let's give now a concrete definition. So the thermomechanical problem is characterized by inherent interaction of the physical phenomena, which are in this case the thermal field, the displacement field. And this interaction happen not only on the surface, but also inside the material. So it happens at each material point. So as I said, the physical quantities interact at each material point, which gives rise to continuum mechanical description by some coupled formulations, as we will see later when we put the covering equation of the thermomechanical problem. And then, therefore, we call this kind of coupled problems volume coupled or materially coupled, because the interaction is at each material point. And we will see later when we put the covering equations and also the constitutive relationship, especially for the stress, we see that we have some specific mechanical terms, specific thermal terms, and then we have coupling terms, and this would be apparent in this constitutive relationship. This was a class of coupled problems. Now we move to another class, which is the surface coupled. So take, for instance, the fluid structure interaction. This might be the air, which is flowing over some structure, which might be a car. So the fluid, which is the air here, is some kind of subdomain, so fluid subdomain. And the car represents here also another subdomain. And they are distinct subdomains. So we have and we have interface between them. So the interaction between each of the subdomains, it happens only on the interface, and this is a typical surface coupled problem. Now let's give a concrete definition. So the surface coupled problems are characterized by distinct spatial subdomains. So we have the subdomain for the fluid and subdomain for the structure. And we have distinct sets of dependent variables. So, for instance, the fluid, it affects with a kind of pressure on the structure, and then the structure will respond through some displacement. So the substructures are only linked through the interface. So they are not inside the material; it's only on the interface. And this is represented by the contact. So if we have like a fluid is flowing on the surface, then we have maybe some kind of shear. and interaction. So you have also normal forces. And this is the interface. Therefore, this kind of coupled problems, as I said, they are called surface coupled, or also called geometrically coupled, because in the space we have like subdomains, and we have the geometry of each subdomain and exactly the geometry of the interface. So it's geometrically coupled. And yeah. So let me now wrap up the issues in like more abstract way. So we are now starting with the 5th section of our course, and I will start by giving the definitions. So for the surface coupled problem or geometrically coupled, we consider, for instance, the fluid structure interaction. I mentioned the car and the air which is flowing around the car. This is one example. The other example might be, for instance, fluid which is flowing inside a pipe. So we have the fluid domain, and the pipe is a solid or a structure. And then we have a distinct interface. So each of the fields or of the materials, they occupy a distinct spatial domain, and the interaction, as I said, between them, which might be friction, might be pressure, it takes place through the interface. Yeah, and for the numerical computation, this type of coupling is well suited to what's called partition solutions. This would be a part of the subsequent video or subsequent lecture, where we can like take each of the subdomains and solve them separately, and then we take the condition on the interface. This is also very good if you are carrying out like parallel computation. You might take the fluid problem on different server and the solid structure on other server, or you can use even a different solver, so a different strategy is a solution, but you have to fulfill all of the conditions on the interface. Now, the second type or class of problems is the volume coupled. In this case, we consider the problem of thermoelasticity. It's a typical example. And also, there are other problems from the field of porous media mechanics, where we have also at each material point, like interacting pressure or interacting like bore fluid and solid skeleton. And then you have the pressure as an interacting or coupling variable. For the like thermoelasticity, this is also another example. So if we take like a solid body, which might be cold, and put it in hot water, of course, at the interface, you have here distinct interface. So if you take this as a fluid solid interaction, it will be surface coupled. But if you observe the increase of temperature of the cold body and then the expansion due to the increase of the temperature, this is volume coupled, because the temperature will change not only on the surface, but also inside the solid body itself. There will be change in the temperature. So it is a volume or materially coupled problem. And in the continuum description, you will, or using the continuum mechanics, you will see later, as I said, some coupling term in the covering equation, which helps us also to understand or to be able to model this issue. And now let me give a general definition of coupled problem. So by definition, a system which consists of one or more subsystems interact with each other, where an independent solution of any subsystem is impossible without the simultaneous solution of the other, is called coupled problem. This is clear, for instance, in thermoelasticity. We have one system is a mechanical system, and the other system is a thermal system. You need to solve both systems, or both, or you have to give like a description, mechanical description of both effects, mechanical and thermal, and then you have to solve these simultaneously. Any change of temperature will give you a mechanical response. Any mechanical response will give you change in the temperature. The same for fluid structure interaction. So one system would be then the structure, and the other system would be the fluid, and then the flow of fluid will give you some change at the interface, and this leads to deformations and so on. So you have to take care of both systems at each time step of your solution. Now I will give like similar example, and the aim here is to show how the coupling appears if you have equations. So at the end, we'd like to give a kind of continuum mechanical description of our systems, or mechanical description in more general, and then we need to see the coupling inside the equations. Take this, for instance, a single mass oscillator. We have a mass, which is mass point. It has a value of m. And it's attached to a spring with a stiffness K. If you plot the free body, then you have on the one hand the m, the mass multiplied by the acceleration, and it is on the left-hand side the reaction, which is the stiffness multiplied by the displacement. In this system, our unknown is the displacement. And then if we look at the second law of motion, or Newton's second law, then we have this balance equation. It's a single equation, and it has one unknown, which is the displacement, so we can't solve it. If you reformulate this, then you have u double dot equals to minus k divided by m multiplied by u. As it is one equation, it's one unknown, so it's uncoupled system. So it's a single balance. And this is a typical example of uncoupled problem. Now, if we increase the complexity of our system, and then we add another spring here, and we cut then the springs to plot the free body diagram, then we can put the reaction forces here, and then we have the inertia force, which is the mass multiplied by the acceleration. According to the Newton's second law of motion, then this is balance equation. Again, we have only one unknown. We need for this one unknown, we need one balance equation, and therefore it's not a coupled problem, it's uncoupled because it's one equation. Now let's add another mass. So now we have a system which consists of two masses. One mass, it has a deformation of u1, and then for the second mass, the deformation will be represented by u2. So now we have in our system two unknowns. If we apply some perturbation or some loads to these masses, then we have these two displacements which have to be determined. It's clear now one equation will not be sufficient because we have two unknowns, so we need two equations. And before talking about the coupled, it's clear if I move this mass m1, then there will be deformation in the spring k2, and this deformation will lead also to a force in the second mass, and then it will be moving in a certain way. This interaction is mutual, so if I also apply some load to mass m2, it will lead to deformation or to the displacement in the second or in the mass which has the name m1. Now, how can we describe this by equations? For each mass, we can put the balance equation, and it's clear that we have u1 and u2. And you see, for instance, in the first equation, which is a balance equation for the mass m1, we have u2, so we have information from the other mass. And if we look at the second equation, which is the balance equation in connection with the second mass point, m2, we see that we have u1, so we have information from the other equation. So it's clear we have a coupled system of equations, and this is a simple coupled problem. If we put these equations in matrix form, then it will be much clearer. So in this case, the two masses M1 and M2 can be collected in what's called the global mass matrix. Then you have U1 and U2 with double dot, so it's like U double dot. And then equals to minus, this is like a global stiffness matrix. We are just collecting these stiffnesses and putting them in matrix form and multiplied by U1 and U2. This is also a vector. Now it's clear the off-diagonal terms represent the coupling. So this K1 and this K2, clear if you go back to this spring, and then if we cut this spring, then we have independent motion of M1 and M2. So which means that if we have this spring, then this is our coupling like factor, and it has a stiffness K2, and this appears in the equation. This like collecting these equations in this form allows us to like simplify the treatment, and then we have u double dot equals to minus n minus 1 ku. So it's like simplified representation of the two equations. So as I said, this represents a coupled system with coupling terms are the off-diagonal terms of K. So again, this is the off-diagonal. And this is corresponding to the stiffness K2. Now, if we cut this spring, it means if we put K2 equal to 0, then we get uncoupled system. So uncoupled system is characterized by 0 off-diagonal terms. Thus, putting K2 equal to 0 yield uncoupled system of equations. And yeah, this is what I said, just remove this spring. Now, let's move to a bit more complicated system or more general like mass spring system. So take, for instance, this system, which is consisting of 3 masses. Actually, you can repeat this structure several times, n times, and you have always like mass spring, mass spring. But for simplicity, let's look at the 3-point masses. These point masses M1 and M2 and M3. The stiffnesses of the connecting springs are K1 and K2. Of course, here we also neglect the mass of the spring. And then we have B, like B1, B2, B3. They are like could be external forces. And as usual, the displacement at the masses, they are our unknown. Now we can have like a general form of the balance equation. So for each mass, here we could have a balance equation of this form. However, n should be replaced by the number of the mass. So if we take n equals to 2, it means we are looking at the mass m2, and this is the like balance equation of this. Now, if we collect this, for the 3 masses, then we have 3 balance equations, and then we can like collect them in matrix form or put them in matrix representation. Then we have a global mass matrix multiplied by global acceleration vector. So it's u double dot, its acceleration. So u1, u2, and u3, and with 2 dot, plus the global the global stiffness matrix. It includes all the stiffnesses, and this is K, multiplied by the global unknown vector U, and equals to B, which is the forces. As we did before, it clear the off-diagonal terms are the like the coupling terms. Now, if we put these off-diagonal terms like K1 and K2, put them 0. So we put Kn and go to 0, which n it would be 1 or 2. Then the motion of the masses will be independent of each other. So as if we cut K1 and K2, we cut them, then each of the masses will move independently, and the motion of any of this mass will not affect the motion of the others. So it's a clear uncoupled system. Other way around, if we increase the stiffness of these matrices, so we put Kn go to infinity, then the mass points will be rigidly connected. It means they will connect with the same motion. In this case, the U1, U2, U3 will be equal and equal to U. And like we don't need then to distinguish between the mass points, so just sum the masses in one mass, and any force which is applied to these masses will be applied exactly to the others. So we will have like a single equation, then it will be also uncoupled system. Okay, so within these limits, it means within the limit of 0 stiffness and the limit of infinite stiffness, we are moving between weak and strong coupling. It's clear if we go to like 0 stiffness, we are in a very weak situation. And then if we go to higher stiffness, then we are in strong coupling. And this is the limits. So with this, I'm at the end of the like first lecture on coupled problem, and this is, was more or less the introduction. In the next lecture, we will address the numerical, some numerical aspects, numerical strategies, and until then, we will meet on Monday. Thank you so much.